Yeah. We're in room 320. Okay, so what we're doing today is we're gonna look at some of the background information in calculus. We're gonna step away from derivatives for a bit and look at. This morning we're looking at just limits in general. So every derivative is a limit. It's the limit as h goes to 0, blah, 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 blah. So it's a good idea to take some time and understand just what a limit is and how they work mathematically. So that's our focus this morning, is solving limits. And then this afternoon we'll look at what it means for a function to be continuous. So this first picture, what we're looking at here, these wonderfully drawn pictures, I want to know if the limits exist at all, and if they do exist, what number are they? So the limit as x approaches 4 of this function here, what do we think? So that is in fact the correct answer there. As x gets close to 4, that function gets close to 5. So that's the answer to that limit. So it does exist. It is the number 5. What do we think here? So as x approaches -2, so as x gets close to this value, what is this function doing? There is a discontinuity there. What does that mean about our limit? Okay. Anyone else have a guess? 5? So I've got one vote for doesn't exist. Yeah, go ahead, Ethan. Mm-hmm. So we have, those are basically the three options. It could be -4, it could be 5 up here, because that's where the function actually is, or maybe it's one of these ones that doesn't exist. And this is one that in fact does not exist. So this is a limit that does not exist. So you can watch the end of Mean Girls when she's in the math contest, and it's a question kind of like that, I think, where the limit doesn't exist. Is that a reference that people still get? Okay, so that's what we're going into. Okay, so what we have here is we have two different things going on. So this notation here where you put the little minus sign, that means it's approaching -2 from the left. So as x gets close to -2, but if we're on the left of -2, then we're on sort of this jump of the function. And we get on the left side of -2, it's approaching the -4. On the right side of -2, so if you're approaching from the right side of -2, you're up on this branch of the function, and you're approaching 5. And it's the fact that these are two different things. One's -4 and one's -5. When we talk about this limit here, if there's no sign there, it means it has to be the same on both sides of -2. It means if you're getting close to -2, you're definitely getting close to a number. So I can't say if I'm close to -2, sorry about that. Just crashed completely. Okay. Oh, now I got two copies. If I'm close to -2, I can't say for sure. I'm still sharing this, right? Okay, thank you. if I'm close to -2, I can't say for sure that I'm close to 5. Because if I take one teeny tiny step off -2 this way, I'm actually close to -4. And if I'm close to -2, I can't say for sure that I'm close to -4, because if I take any teeny tiny step off this way, I'm way up here at 5. So the fact that these things are mismatched means that this limit doesn't exist. Whereas what these are called are one-sided limits. The one-sided limits exist, and they have values, but since these values don't match the overall limit, we say does not exist. Everyone good with that idea? Okay. Last one here. As x gets close to 14, so there's a hole in the function at 14 there. What do we think about this limit? Exactly. So what this says is we're going to get close to 14. We never actually get to 14. We're just seeing what the function gets close to. And we can say definitively on this one that it does in fact get close to 20. Doesn't matter. As long as you're getting very close to 14 for x, the y value will be very close to 20 on both sides of 14. So that one does exist. It doesn't matter what happens at the value 14. So even if there was a dot up here where it was kind of filled in, the limit would still be 20. Because on both sides of 14, but not at 14, we're close to 20. All right, so I'll write this up as a non-formal definition. The formal mathematical definition of a limit is something that you might look at in first-year university, depending on which program you're in and whatnot. We only do a non-formal. I can, for funsies later, write out the formal definition if you want to see it. But the non-formal limit as x approaches a of f of x equals L if you can guarantee f of x, which we can think of as the y value, will be close to L. So L is just some number. I'm using L for limit. You can guarantee f of x will be close to L by making x get close to A. And then I'll specify x can get close to A on either side of A, the left or the right side of A. So now instead of looking at pictures, let's look at functions and see if we can figure out some of these limits. Sorry, I'll leave that up there. Are we good to move? Okay. So the limit as x approaches 3 from the left of x squared minus 6. What do we think? Okay, so a couple people saying 3. Anybody got any other numbers, or anyone want to justify why it's 3? So how do you know you're allowed to do that? Just put 3 in here. Yeah, so you kind of, there's nothing weird going on at 3 on this function. This function's a parabola. There's nothing weird going on. So as x gets close to 3, like it's going to get close to wherever the graph is, and the graph happens to be at 3 there, 9 minus 6. Okay, so that's a parabola. There's nothing weird going on there. We can just plug in, get an answer. What about this one over here? The limit as x approaches 0 of the square root of 3x minus 64 over x minus 4. Right, so in a square root function, only half of it's showing, so just regular square root, because you can't square root a negative. So at 0, is that going to be a problem for this particular square root function? Well, as x gets close to 0, what's all this stuff approach? That's the key thing here. Well, we can kind of try and figure it out. You'd get 0 minus 64 over 0 minus 4. You'd get negative 64 over negative 4. You'd get positive 16 when you divide those. And you can get an answer there, and it's 4. So what do we think? Is that good or is that not good? Here it doesn't matter because when x gets close to 0, the thing inside the square root is close to the number 16, positive 16. So either side of x being 0, we're probably going to be on either side of positive 16. And either side of positive 16, like on this graph, just plain old square root of x is way over here, is that kind of point. And so positive 16, there's nothing weird going on a square root graph at positive 16, which means there should be nothing weird going on in this graph when x is 0. So this isn't this graph, right? If we want to see this graph, right? So this particular function is pretty funky. Okay? But at 0, right? Zoom in at 0, nothing weird about that function. Right? So when x is close to 0, the thing inside the square root is close to 16. And square root of 16, there's no issues there. There's no problem there. We're going to get an answer close to 4 if we're close to 0. If we were taking the limit as x goes to, oh, I don't know, 4, we'd have a big problem, right? Because that's the asymptote on this graph. Vertical asymptote. So that limit for sure would not exist because on the other side of 4, we get this whole gap in here where the inside must be negative because the graph's not even appearing. So anything from 4, any of these values, we wouldn't have a limit because we don't have a graph up until apparently 21.333 is where this thing starts appearing again, where the inside of the square root becomes positive again. But the fact that this is positive 16 when I plug in 0 means that this limit's going to be good. There's not going to be an issue here. Yeah, pretty much. So these are what I call no problem problems. Okay? There's nothing wrong with the function at the particular limiting value these are called. There's nothing weird going on. So if you can plug in and just get an answer, that's going to be your answer. However, if we had x approaching 4, if I plug in 4, I get 0 on the bottom here. That's a problem. I'd have to think about, is there something going on that I can actually get a value here or not? If I had x approaching like 10, I'm pretty sure that's one of the values that makes this negative. Yeah, you get positive on the bottom, but negative still on top. That would be a problem. Yeah, Rachel? Yeah, and it might mean that it doesn't exist, and it might mean that the limit still does exist. You have to do some more analysis, right? Because if you plug into a function that's got a hole, if you just plug in the value, you're going to see that there's no answer there. But that limit can still exist. So when you don't get an answer is when you have to do a bit more work and see, is it a hole? Is it an asymptote? Is it just there's no function in that area at all? Is it not part of the domain? That sort of stuff. And we'll get into those later this morning. Any questions about the no problem idea though? Sweet. So now I'm going to look at my next sort of wrench that I can throw at you is these piecewise functions or branch functions. So g of x is the straight line for x minus 2 for all x values below negative 2. It's this parabola for all values between negative 2 and 3 and including those two endpoints. And then it's this rational function after 3. So my first question is, what's the limit of this function? Oh, I called them f's down there, so I guess I better make that an f. What's the limit of this function as x gets close to 4? Okay, and how are you getting that? So let's not worry about calculating the answers. Let's just talk about what the first step would be. Yeah, so absolutely. We can say for sure if x is getting close to 4, we're definitely on this final branch of the function because we're nowhere near the jump, which is 3. So if I'm approaching 4, I for sure know that it's really going to look like the limit as x approaches 4 of this function. And yeah, that function, we can try it, but yeah, you are allowed to plug in 4 to that piece of the function. And you do get an answer here. So yeah, I think it's 50 on top and 16 minus 9 is 7. So yeah, we can leave it as the fraction 50 over 7. So that limit exists. It's good. And that's sort of the easy one of these. And now the next one, I'm going to say what happens as x gets close to negative 2? So what's different about negative 2? Why is this one a bit trickier than just approaching 4? Yeah, it's the transition between the straight line to the parabola. And the question really is, does it look like this? And then it switches to parabola, but they stayed at the same point? Or does it look like this and jump to somewhere on the parabola? So how do you think we'd figure that out? Where the parabola and the line intersect? Right. That's one way to do it. That's way more work than what we actually need to do. What else could we do? Right. I don't really, yeah. And that's less work, right? I don't really care where they cross. I just care, do they cross at -2, right? That's what we really care about. So we're just going to plug -2 into each side, into each piece, and see if they're matching or not. And like from a calculus standpoint, really what we're doing is we're doing the limits from the left and the limits from the right of that number and seeing if we get the same answer. So if I'm on the left side of -2, I know for sure that I'm on the straight line. And if I know for sure that I'm on the straight line on the left side of -2, straight line's no problem. I can just plug in -2 to the straight line and get -10. And I know for sure if I'm on the right side of -2, then I'm on the parabola. And parabolas aren't a problem. Let's see, 4, 12, minus 12, 0. Did I do those both right? So assuming I did that right, what's our conclusion then? Yeah, therefore, limit as x approaches -2 of f of x does not exist. Left and right limits don't match. How would these left and right calculations change if the equal sign was on the line instead of the parabola? So if it was this and that, how would this limit change? No, I wouldn't change at all, right? So it doesn't matter what the function's actually doing at the value -2. Doesn't matter at all. You could even not have an equal sign on either of these, and there's like definitely a hole there, whether it jumps or not, doesn't matter. These calculations, the limit would be the same. So what I want to do next is the other jump point. See if the limit as x approaches 3, so that's the other branching. You're either on the left, you're on the parabola, on the right, you're on this fraction. Let's see if those line up and see if those match. So I'll give you a couple minutes to jot that down on a piece of paper. See if you can make a solution that looks like this for that example. I'll give you a couple minutes head start. Okay, so I'll start to walk you through. So from the top, we're doing the limit as x approaches 3. We look at this function, and there is, in fact, something weird at 3. It jumps from one track to the other at 3. So there's something weird going on. We got to do a bit of work. We can't just plug in 3. So we kind of think about the left side of 3 and the right side of 3. And just from a communication standpoint, what's happening here is I'm taking the limit as x approaches 3 from the left of f of x. The logic that I'm applying is that if I'm on the left side of 3, then I'm still on the second branch of the function, the parabola branch. So I can replace f with just the parabola. And now I know the limit as x approaches 3 of a parabola, I know I'm allowed to just plug in 3. So at that point, I'm now evaluating the limit between lines 2 and 3. When I plug in 3, I'm saying I've established that I'm allowed to plug in 3. So that's the step where I've actually done the limit here. So that's where I stop writing limit as x approaches 3, as soon as it becomes 3. And then from there, I do the math, and I got 15 as my final answer there. Ditto on this side, the limit as x approaches 3 from the right of this function. If I know that I'm on the right side of 3, I know that I'm on this branch of the function. And I take a quick look, I plug in 3 is really what I did to make sure, and I see that I am in fact going to get an answer when I plug in 3. So it's not the vertical asymptote, which would be a problem. But so once I plug in 3, I stop writing limit here. I've done the limit now, and now it's just some arithmetic. And I get 45 over 3, and I get 15. And then I have 15, and I have 15. What's my conclusion? Yeah, so this limit is 15. So by giving that limit an answer of 15, you're automatically saying that it exists if you're saying that it equals a number. So this limit exists, it is 15. And I'm pretty proud of myself for coming up with a jump from a parabola to a rational function that was in fact still continuous. Okay. And then so I want you to draw any graph with these properties. The g of 3 has to be 2. The limit from the left of 3 has to be -1, and the limit from the right of 3 has to be 4. So see if you can take a minute, see if you can draw any function that kind of does those three things. Maybe if you're feeling brave, you can send a picture of your drawing to the Google chat. How are we doing out there? Do people have pictures? Alright, so let's figure this out in parts. So what does this first instruction say? G of 3 equals 2. What's that say that my drawing has to have? Yep, so it's got to have that solid filled in circle at 3, 2. Because that's where the actual function is at 3. It's at 2, so we need that dot on the graph. What's the next instruction say? As we get close to 3 from the left, the function has to approach -1. What does that translate into? And then what did you do with that circle? Yeah, so you need to have the function over on this side of that open circle. So it doesn't matter what it looks like, but it needs to be over here somewhere. And then the last instruction is going to look like what? And then the function coming out on the right side of 3, 4. Okay, so I hope your picture looks something like that. Any questions about that example? Or anything I've done? Because the function has to be here at 2, which means it can't be anywhere else. Yeah, if this was also a open filled in circle, then we would fail the vertical line test to not be a function. Okay, so I've got 5 examples here and then some consolidation, taking stuff up. Do we want to take a 5-minute break? We've been at this for a bit. Okay, any objections to powering through? Okay, so let's power through then. So these are all going to be a bit weird, and we'll see why they're weird, and they're going to be something called indeterminate forms. But our first one here, limit as x approaches 2 of x plus 6 over x minus 2. What's going on there? Yeah. So if I plug in 2, what I end up with is 8 over 0. And I'm going to put that in quotes because we're not allowed to do that, right? So what does that mean about this limit? Okay, why? Wonderful. I shouldn't write equals. I should just write does not exist. So we know that this one doesn't exist because there is that vertical asymptote. So there's 2. Don't know exactly what it looks like, but you know, whatever it looks like, right? There's a vertical asymptote there. So that graph is definitely not getting close to a number. It's exploding off to infinity, positive or negative infinity. So as soon as we know that the limit's going to infinity, it's not getting close to a number, we can write does not exist right away. Any questions about that one? Okay. So limit as x approaches 2 of 4 minus x squared over x minus 2. What's happening here? Okay. Why? Like, why would I want to do a difference of squares? What happens when I plug in 2? Right. So what happens when you plug in 2 is this one also doesn't work, right? If you plug in 2, you get something different though. You get 0 divided by 0, which is wildly different than 8 divided by 0. 0 divided by 0 is what's referred to as one of these indeterminate forms. We don't really know what's going on. And to put it into your advanced functions, this graph might have an asymptote at 0, and it might have a hole at 0, right? And in terms of this limit, if it's a hole, the limit would still exist. If it looks like this, it still exists. If it's going off to infinity, it won't exist. So there's still work to do here. And you're right, we can factor with a difference of squares. Now what can I do? Does that help us see, is it a hole or is it an asymptote? What do you mean by the 2 minus x? Like, what do you want to do with that? You're right, I just want to clarify. Okay, do these divide out directly? Do these cancel out directly like that? Okay, what happens? Right, but they're definitely related, right? So there's 2 ways to handle it. Who remembers how to handle it? Right, so that's the first way, is before you think of canceling, factor out a negative 1, and then that becomes negative 2 and positive x. 2 plus x, x minus 2. And then these are exactly the same. You've got a positive x and you've got a negative 2. And then from there, you would be allowed, now that you've canceled out, it's the same kind of idea as a derivative. Now that we've canceled out a 0 on both top and bottom, the thing that was going to 0, we can now try and plug in and see if we get an answer. And in fact, we do get an answer. So I can take the limit and we'll get negative 4 as our answer. That's one way, is factor out the negative. The other way is I'm fine with you dividing these out and putting a negative 1 in. 2 minus x and x minus 2, they're the same number. They're opposite signs, right? 2 minus 3 is negative 1. 3 minus 2 is positive 1. 2 minus 10 is negative 8. 10 minus 2 is positive 8. They're the same number off by a negative. So when you cancel them, you get a negative 1. So you can show this step in 2 ways. You can factor out a negative, or you can just cancel and drop a negative 1 if you're comfortable with that. Okay, so that limit does exist, and it is -4. Any questions on that one? Absolutely. If it's 0 over 0, that's when we're going to look to try and do something to cancel out a 0 on top or bottom. It's same thing as when I was saying um, like everything without an h has to cancel so that you can cancel that h on the bottom. Every 0 over 0 limit, there's a way to kind of get it so that you can cancel out the 0 on top or bottom. There has to be a way. There's a 0 hidden in both things somehow. And with 0 over 0, you can't decide what it is until you've done that. Yeah, if it's a number over 0, then it's definitely like a vertical asymptote because this is right as this gets close to 0, 8 divided by 0.00001 is 8,000 or whatever, 80,000. It's getting bigger and bigger as x gets closer to 0. So this is definitely going off to some kind of infinity if it looks like this. And we can say right away it doesn't exist. This is where we need to be careful. And my sort of example of why it's called an indeterminate form is this limit here, x squared over x as x goes to 0. Well, you'd cancel an x. You just get the limit as x goes to 0 of x. You'd get 0. If it's just x over x, the limit as x goes to 0. These cancel out, and you get 1. But if it was the limit as x goes to 0 of x over x squared, you'd cancel that, you'd cancel that, you'd get 1 over x. 1 over x has an asymptote at 0. This one doesn't exist because it's going off to infinity. So something that's 0 over 0, it could be 0, it could be going off to infinity, it could be going anywhere in between. That's why we say it's indeterminate. You have to figure out what it's doing before you say what the limit is. All right. Next one, limit as x goes to 3. Well, I know it's already going to be a problem because 3 minus 3 on the bottom makes 0 on the bottom. That's a problem. I'll plug into the top and see if that's also 0 before I do too much work, because if I don't get 0 on top, I just write d and e and I'm done. So I plug in on top 9, minus 3 is 6, minus 6. Oh shucks, this is another 0 over 0. How do I handle this one? Haven't done the limit yet, so write limit as x approaches 3, multiplies to -6, adds to -1. Nice. I like these types of questions because if you know it's 0 over 0, you can be pretty darn sure that one of the factors is going to be the same as the factor on the bottom, or similar to it anyway. So if you're having trouble factoring, you can use that as a bit of a hint. But those do, in fact, cancel out directly here, the exact same signs. Oh, I'm just left with x plus 2. I can do that limit. That limit is 5. If it's 0 over 0, you'll be able to cancel at least once, right? And then it's not, possibly it's not going to be 0 over 0. I could have made this question this, though, with an extra x minus 3 on the bottom. Here I factored, I've canceled, but now I would have 5 over 0, and it's still an asymptote, right? So after you cancel, you look again and see, is it still 0 over 0? Is it just a number, or is it a number over 0 after that? Does that clear that up? Awesome. Okay. Limit as x goes to 0 of the square root of x plus 4 minus 2 over x. Okay, so definitely the bottom's going to 0. Plug into the top, I get root 4, which is 2, minus 2. Oh, crumb, that's also 0. So we've got another one of these indeterminate forms. We can't just plug in. This is a 0 over 0. It's got a square root in it. I wonder what we do there. Yeah, what did we do yesterday? When we had roots yesterday, what was our trick? Right, so it's called multiplying by the conjugate. So I'm going to multiply top and bottom by, change that to a plus. Do I change this plus 4 to a minus 4? No, because we want a difference of squares. So the stuff inside each sort of term stays the same, and it's just the middle sign. So that would be a mistake that I would see people do, is they like change every sign that they see, and that's not what you're doing. You're just changing the sign between the two things. Now here's the next thing. So if you don't want to make a mistake, you can fully expand the top, do that times that, that times that, this times that, and that times that. But again, since we've set this up as a difference of squares, we don't have to do all that step. We know that we're going to get a squared minus b squared. So the a term is the square root of x plus 4. So I know I'm going to get x plus 4, the square root of that squared, which is now just the square root's gone. And then I'm going to get minus 2 squared, which is 4. Okay, so the mistake I would see is people would leave this as a negative 2, because they're used to this being also a square root from the examples from yesterday. So it would be negative 4 from negative 2 times positive 2. And then the middle terms cancel. Negative 2 times the root, positive 2 times the root. Those cancel out. Haven't done the limit yet. Got to squeeze it in front. And my check that I've done that right, that I haven't made one of those mistakes where I turned that to a minus or I didn't square the 2. The check is here. If I plug in 0, I have 0 on the bottom, and I still have 0 on the top. I have 4 minus 4 on the top if I plug in 0. And that makes sense because we haven't done anything to cancel out the zeros yet. It should still be 0 over 0. We've just multiplied top and bottom by the same thing. We haven't done any canceling yet. So that's my check that I've done that correct. But what we're left with is the plus 4 and the minus 4 cancel each other out. And then I just have x on top. I have this x on the bottom. I didn't bother expanding the denominator. There's no reason to. You want it factored anyway. Now that that's canceled, these x's can cancel, leave the 1 on top. That's a lot of mess, but I'm saving myself a line. Now I've canceled the 0. Now I'm going to try and plug in 0 and see what I get. And I get square root of 4 here. So that's 2, but now it's a plus 2, so I get 4 on the bottom, which is fine. So I can get my answer of 1 over 4 as a final answer there. Any questions on that example there? Just equals 1 over 4. That's fine for a final answer. It's a bit different than this question. Why I wrote it differently for this question is to get to this answer, I had to do two separate calculations. And then I'm making a conclusion that is, since these match, I get an answer. And this is my answer. So I kind of have to do like a therefore statement here. This question, it is kind of a continuous work down the page. I've shown that I'm multiplying top and bottom by the conjugate. I've done all my canceling. I've plugged in 0, and I've gotten my answer. It's a single flow from question to answer. I didn't have to break into two. Okay, last one until I talk about a bunch of other stuff. Limit as x goes to 0 of the cubed root of x plus 8 minus 2 over x. So I see right away the bottom 0. Plug in 0, I get the cubed root of 8, which is 2 minus 2. Oh, shucks. 0 over 0. I got to do some work. What do I do here? Wonderful idea. So that's one way to handle this problem. What I want to point out is this trick won't work because this is now a cubed root instead of a square root. So when I do expand this out, it doesn't get rid of it. I'd get x to the 2/3 if I did cubed root times cubed root. So that's not going to work. So one way to do this, very good idea, is to create a difference of cubes, which is a bit strange. So I'll do it that way. I also want to show you a different method entirely that we haven't talked about. So I'll show this one two ways. So difference of cubes. The other method I want to talk about is called a change of variables. Okay, so this is a technique that's used in calculus quite a bit, especially in university, but in high school calculus, this is pretty much the only spot where we'll see it. But I do kind of want to introduce you to this idea of a change of variables as sort of a new technique because it's sort of very versatile. It can get you out of a lot of jams. So we've established that this is 0 over 0. We look and it's not a normal square root, so our multiply by the conjugate won't work. Like it's not a rational function. We've got tricks to do a common denominator there. That's not going to help us here. The change of variables basically is a catch-all. If none of your previous tricks work, we're going to try a change of variables. And what that is, the best way I can describe it is you make up a new variable that is whatever the weird thing in the question is. So what's the weird thing in this question? The cubed root. So I'm just going to take just the cubed root. I'm going to take the cubed root and just replace that with u. And now, why that's nice is that the top would then just be u minus 2, and that's no longer scary, right? So we're kind of hiding the scary thing inside of another variable. If I leave that bottom as x, well, I'm going to be stuck because I'll have u's and x's and I'll never be able to make it cancel with two different types of variables. So what we kind of have to do now is rebuild this limit piece by piece. And so since this limit has an x in it, I'm going to take this and rearrange for x. So I'm going to get rid of the cubed root, I'll cube both sides. And then I'll rearrange for x, and x is going to become u cubed minus 8. So this is all my work before I rebuild the limit. So the bottom used to be x, now it's u cubed minus 8. Now, our limit was as x goes to 0. And again, that's not helpful because this is an x and these are u's. I don't know what u does if x goes to 0. So what I want to do is figure out if x goes to 0, what is u approaching? So the easiest way to see it is in this line, the initial line actually. As x goes to 0, what's u approaching? Two. If x becomes 0, this becomes the cubed root of 8. U is going to 2. So we've taken that. Basically, we've hidden the thing that we don't like inside of u. We've rebuilt the equation. We can rebuild it. We have the technology piece by piece so that everything now is u's. And we look at this one, and this limit will have the same answer as this limit, but this limit is much less scary. Still with me? So basically the idea is you take the scary thing, cubed root of x plus 8, and you just make that a variable of itself, so a u. And so the top becomes u minus 2. Now we need to take the rest of the equation that we had, or the limit that we had, and try and write it in terms of this u instead and hope that it's better. It might not be better. So this equation had an x. So I'm going to take my u equation and solve it for x. And I get x equals u cubed minus 8 after I rearrange. So the denominator used to be x. Now it's this u cubed minus 8. So I've rewritten the whole fraction using this u. And then it's just a matter of x was going to 0. If x goes to 0, this u variable is going to go to 2. So that replaces everything that was x is now this new u. It's crazy. I totally admit that this is a crazy concept. Now, if I plug in 2, what happens in this limit? Still get 0 over 0, and that's a good sign because we haven't done anything. We've just rewritten it with different variables. It should be exactly the same still, so that's a good sign. That's another check that I haven't messed that up. If all I did was do the change of variables and it wasn't 0 over 0 anymore, I know that I've screwed up my change of variables. But this looks more like the things that we've dealt with before. So how do we factor the bottom, basically? Yeah. So it is a difference of cubes. A cubed minus b cubed. Anyone remember that formula? Anyone got that one memorized? I believe so, yeah. And that's one that on a test or whatever, I'll make that formula available. It's one that I often have to Google, but I'm pretty sure that's got the plus signs in the right spot. Okay, so RA is u, and our b, if 8 is b cubed, then our b is 2. So I'm just going to write that out. Limit as u goes to 2 of u minus 2. That first bracket is going to become u minus 2. I'm already happy because I see that it's going to cancel out in a second. The next bracket is a squared, so that's u squared. AB, that's 2u, and b squared, that's 4. But the u minus 2's cancel, leaving a 1 on top. And then I can just simply plug in 2. I got sidetracked looking at what I'm going to do next. I get 4 plus 4 plus, this is a 4, not a u. Which is 1 over 12. And there's my final answer. Any questions about that? Okay, so now let's go back. Let's take the initial suggestion was turn it into a difference of cubes, and it's an excellent suggestion because how we dealt with square roots is we turned it into a difference of squares. So if I'm going to make that my a minus b, this bracket needs to be this. So I would need to put the cubed root of x plus 8 squared. There's my a squared. I would need to do plus 2 times the cubed root of x plus 8. Let me zoom in over here so I can. There's my AB. And then the last thing should be b squared, which would be 2 squared, which would be 4. So there's my a squared, my ab, and my b squared, if that's a minus b. Same thing on the bottom. So this is the analogous thing to, put brackets there, to what we do multiplying by the conjugate. This is the cubed root version of multiplying by the conjugate. And since I've set that up as a difference of cubes, I know that I'm going to get my a cubed minus my b cubed if I expanded that all out. I'm not going to bother expanding it. I know that's what should happen. And then I'll get the cubed root of x plus 8 squared plus 2 times the cubed root of x plus 8 plus 4 at the end there. And here's the neat thing, cubed root makes the cubed root cubed makes that go away, so you get just x plus 8, you get minus 8. I get all of this stuff one more time. I'm out of space, but the minus 8 and the plus 8 cancels, which allows the x to cancel top and bottom, leaving a 1 on top. Now we've canceled out the 0 over 0. We would be allowed to plug in. And look at what happens. You get 1 over, this becomes the cubed root of 8, which is 2, squared, which is 4. This becomes the cubed root of 8, which is 2 times 2, which is 4. And we have that plus 4. We get that exact same, shouldn't write limit anymore, 1 over 4 plus 4 plus 4, still 1 over 12, and we never did a change of variables. So this technique is the technique I wanted to show you. I think this one's interesting because it uses the same sort of idea as our last technique, and I think it's very neat that when I did a change of variables, it turned into a difference of cubes. And here I had to use difference of cubes, and somehow I ended up with the exact same formation, 1 over 4 and 4 and 4 to get to the 1 over 12. So I just think that parallel's neat. So this technique, making it a difference of cubes, will work anytime you have a cubed root. That should work. This technique is a bit more versatile. If you have anything, you can try a change of variables. And the thing about change of variables is sometimes you've rebuilt it and you find that you still can't solve it. And what you have to do then is maybe make a different choice for your u variable and try again and see when you rebuild it if you can solve the new version. So there can be a bit of trial by fire there. I'll tell you now, just to, because I know this is crazy looking. Change of variables, wonderful technique, something that you will do all the time in university calculus. If you take university calculus, that is. There are some questions in the practice that require a change of variables, but I'll tell you that on my tests there aren't any limits that will require a change of variables. The test questions will fall into one of these four type of things. Okay? Still with me? Okay. This was a long lesson. This was normally 2 days worth of stuff that I crammed all into this morning, so I apologize for that. What does it mean about the function? So if the limit as x approaches a of f of x equals n, what does that mean about the function? It means y is guaranteed to be close to n if x is close to a on either side. So that's just sort of restating that non-formal definition. If a limit doesn't exist, what might that mean? Might be an asymptote. Two people were speaking. I think they both said asymptote. What else might be happening? Yeah, so a jump, discontinuity. Words are tough. So it might look like this. Might look like that. There's other options, but those are kind of the main two that we're going to talk about. Someone want to take a stab at what's a no problem problem limit and how do you solve it? Zero over zero is the indeterminate form. No problem problems are what we did before that. Yeah, nothing weird in the function at that x. Just plug in x and get answer. So that's like the limit as x approaches 4 of x plus 2. X plus 2 is just a straight line. We know that that's going to get close to 4 plus 2, 6. That's what I call a no problem problem. Okay. So these limit properties are kind of like the basic building blocks of limit that say everything that we want to do with limits we're allowed to do. So they are pretty important. They seem weird just to write them out, but it's good to have them. So whenever we have a k in here, that's just going to be some number. So the limit as x approaches some number, so let's say the limit as x approaches 4 of the number 5. So what does k get close to as x gets close to a? So as x gets close to 4, what's the number 5 get close to? 5. So this is just going to be k. This number doesn't care what x does. X can go anywhere. 5 is 5. That's what that limit property is saying. The limit as x approaches a of just plain old x. What do we think there? Yeah, as x gets close to a, x gets close to a. Like it is this silly thing, but I'll show you how we put these all together in a second. This limit property says if we have two things added or subtracted, we can think of that as the limit of this plus the limit of this. So if you have the limit of two functions added up, you can get the limit of each function separately and add up those two answers or subtract those two answers. That's what that property is saying. This rule gets a star. I have to put an asterisk on that rule. Anyone have any idea what sort of limitation I have to put on that? When that might not work? It's been a long morning and your brains are tired, so I won't push you too much more. You can only split it into two separate limits if the two separate limits in fact exist on their own. So if this is a number and this is a number, then you can split it into two limits and get your answer that way. It's possible for this limit to exist, but for one of these not to. Very easy example of that would be 1 over x minus 1 over x. I can't do the limit as x goes to 0 of those things separately, but I can, since in the limit x isn't 0, I can just subtract those and get 0, but separately the two things wouldn't exist on their own. If there's a constant inside times a function, you can kind of factor that constant out, get the limit of the function, and then multiply that answer by that constant. If you've got two functions multiplied, you can split it into two limits and take the limits separately and multiply those two answers. Again, provided that those limits exist. If it's division, you can split it into two limits, get the limits of the top, the limit of the bottom, divide those two answers. Again, provided that those two limits exist. And this one gets a double star, so long as that bottom limit isn't 0 as well. And then this last one, if you've got a function to an exponent inside the limit, you can get the limit of the function and raise that answer to the exponent. All of that seems crazy, but basically it's what says a no problem problem. You just plug in and you get your answer. So if I have the limit as x goes to 4 of x squared plus x plus 4, I could in fact split that into three limits. This is what I mean by their basic building blocks. And then the limit as x goes to 4 of 4, that's the first property. That last one's just 4. The limit as x goes to 4 of x, that's the second property. That one's just 4. And this one is actually this bottom property. I can do the limit as x goes to 4, which is 4, and then take that answer and raise it to an exponent. So it's these rules combined that let you do a no problem problem. So I just wanted to state them formally. Okay, are you still with me? Okay, I'm gonna stop talking. Okay, so I will leave these boxes for you to make your own kind of notes for. So if it's number over 0, you're just gonna write does not exist. Okay. If it's 0 over 0 with a polynomial on top and bottom, so a rational function, this one's where you factor top and bottom and try and cancel. Square root was multiplied by the conjugate. Okay, you can make some notes on how to do that. And this bottom one, I'm getting at the change of variables. Okay, so I'll leave you to make your own sort of notes on those. Just looking back at the examples. If you need help filling out any of those, I can help you fill those out. For practice, it's broken into 2 parts. So the first page is more of the no problem problems or the branch functions or looking at pictures types that we had at the start. And I've got answers to those questions there. And the second page is more of the indeterminate forms where you might have to do some factoring or some multiplying by the conjugate, that sort of stuff. Okay, so it's split into 2 parts. Again, this used to be 2 lessons worth of stuff. That's why it's taking so long. And so I'll leave you the rest of the morning to work on these 2 pages and to make your notes in here. I'll post what I have so far up to the classroom shortly. We'll meet back again, so I'll leave the meet open. I'm going to take a couple minutes, but I'll leave the meet open if you have questions. We'll meet back this afternoon to talk about Skill 4. Skill 4 is much quicker, okay? So there's much less to do this afternoon, so I kind of front-loaded today. So you'll probably have time this afternoon to keep working on these 2 pages of practice as well. Okay?